Minasan, konnichiwa, Samurai Engineer. So in this video, let us move on to discussion of next module, module 05. It's about structural steel design concepts. Okay? So we will summarize all the concepts involved under part 1, which involves what? Module 1 to 5. Okay? So let's continue. And starting with the objective of the course, PSD provides fundamental concepts, principles, and theories under structural analysis and design of steel elements in an structure. So we have 8 main topics or parts in this course. We are currently on the introduction, but as you can see, we are on the last module under this part 1. So computers and structural steel design. So again, where and when we are gonna use steel structure. So there are several that we learned so far. So from the very start, we talk about span structure, multi-story, high-rise building, buildings of heavy-duty plants, towers, mast structure. We have example of those. Portal frames that we can relate to when we studied theory of structure. Bridges, infrastructures, deployable structures, generalized structure, which are actually more or less mechanical, sort of in the boundary of mechanical and civil engineering. Okay. This could be classified into 2. So we have what the building application and bridges application. At the left side of your screen, you can see a list of samples under building application. So we have trusses, structure, either bar or truss members. We have frame structures using beams and columns, grid structures or latticed structure or dome, which is somewhat, if you observe, similar to trusses, but there is what? Some particular difference, particularly lattice is now analyzed using 3D rather than 2D. Okay? So arch, and lastly, pre-stressed structure, which we only explained, but we will tackle as a separate part in this course. Okay? And as you can see on your center or on your right-hand side, you have what? The bridge application. We have beam bridge, we have truss bridge. So there are truss members, bar, or component which form parts of assemblage of trusses under also the bridge structure. We have arch bridge, we have cable stayed bridge, and suspension bridge. So those are the things that we talk about, discussed in this part 1, which we emphasized. And now we are going now how to make our steel to be used and applied appropriately, okay, on those applications. So steel design, meaning structure or structural components primarily made of steel members attached to each other appropriately. So there's an assembly of components attached to each other. So there are joining of components, joining of members. Okay? Steel is an excellent material in both tension and compression. That's correct. It is one of the emphasis we gave to you in one of our previous module. Since steel is primarily made of thin plate-like elements, they are susceptible to buckling, local and otherwise. Okay? So, lastly, since they have to be joined together, connections in steel are considerably different. Okay? When you are using other materials, okay, like concrete and what wood. Okay? In steel, the members are discrete or ruled, meaning hot rolled or cold rolled. Okay? Fabricated, that is the meaning of it, separately and are attached to each other using appropriate connection like what rivets, bolts, pins, welding, and so on. Okay? And what can we learn about this in order to transition us to the application, to the problem solving? We need again and again to be reminded of this stress strain curve. And for the first time, we have a stress strain curve that is actual characteristic of certain common structural steel. So we have here what? There are three. There are three types of structural steel here. So what we say, A36, A572, and A514. So these are three types of structural steel. So A36 is known to be a carbon steel. A572 is known to be high strength, low alloy carbon steel. And A514 is known to be heat-treated construction alloy steel, which is quenched and tempered. Okay, so this is actually the topic of the viral video claimed by Engineer Emil Morales and Senator Cosoteng. So TMT produced type of steel is actually what we call quenched and tempered alloy steel. This is specifically the type of material. And you can see the difference in stress level, the capability. So the capability of A514 is comparatively high with respect to A572 and A36. So A36 is the base, so the basic capability, the basic tensile strength, the basic yield strength of structural steel. That is the basic form. And actually, that is the most popular up to some time in recent past. Okay. However, just recently, the 50 KSI yield strength type of structural steel is now in common use, and even in what? In the code. Okay. For example, this particular graph is actually the graph of these particular products and taken off from the AISC code 360-2016. Okay, or code 360-what? That's 1996. Okay, this. However, the characteristic of steel doesn't really change, even if they are discovered a long time ago. So the improvement will be carried out and renamed. Okay, it will not be updated to the same name. Okay, to the old name, but it is renamed for new standard. Okay, so just like what I've said here, we are now using currently the A572 or A599. I think that is the same. So that is called high strength, low alloy carbon steel, and 50 KSI yield strength capacity. Okay, take a look. That is only 50 KSI capacity. If you do the additional process of TMT, okay, you can what? You can make it double the characteristic. Imagine that. It is now 100 KSI, quench and tempered alloy steel. 100 KSI, only 50 KSI here. Huh? 100 KSI. Okay? So in our SI unit, so in our country, we are using SI unit. So yield strength of 50 KSI is about 345, what? 345, I think 345 megapascal. Okay? So, 345. So therefore, this is what? 690 megapascal. Because that is what? Times 2. Okay, and 836 is about what? 400, what? 200, what? 345, this is 280 or something. 280 or 275, something like that. 836. Okay. So these are actual and from the code. So it could be used in the design. Okay. So let us look back at the temperature effect on the steel. Okay. So as you can see, A514, A572. This is the high strength, low alloy steel. This is the common steel, A36. Okay. So they all suffered from the effect of temperature if the temperature is about 500 to 550. Okay, here in this form. Okay, substantial decrease in their capacity is noticeable in this graph. Okay, very noticeable in this graph. So, effect of temperature on yield strength. So, about what? 90 for 500 degrees Celsius. Your what? Yield strength is what? Decreased, has decreased by 10%. Okay. So if you go further to what? 800, so it is what? 20% decrease. So it's too much, no? It's too much. So there is a real effect of temperature, and actually the steel strength suffers greatly, and therefore temperature is the one of the enemy of steel, and so is the water. So that is the two great enemies of steel: water and fire. Okay. High strength steel. So right now we are currently using yield strength of 50, but ultra high strength with yield strength of 160. So from the graph we have what? 100 KSI, but now they are studying different steel material. They are researching 160 to 300 KSI. There are more than 200 types of steel, okay, products. 200 different steel products, okay, exist on the market that provide yield strength. So there are what? There are about 55 countries who produce steel products. Okay? So it is not impossible to have about 200 different steel products in the market with yield stress in excess of 36 KSI. So 36 is the base yield strength. The steel industry is now experimenting with steels with yield stresses varying from 200 to 300 KSI. Probably steels with 500 KSI yield strength would be made available within a few years. Okay, so this is 2016 document. So maybe today, I am not aware. We can search. So assignment. Please research What is the current highest strength steel? What is the yield strength of the steel nowadays? Okay. So the theoretical binding force, because of this, the theoretical binding force is about 4,000. That's why they think that it's still available, possible, still feasible to make the steel product with about 500 KSI yield strength. Take note, 4,000 KSI. Okay. So what is 4,000 KSI? That is the estimated binding force between iron atoms to another iron atom. So that is what we call what? Metallic bond. The metallic bond is about 4,000 KSI between ion elements. So let us talk about the details of possible failure of the structure. It was mentioned that the collapse of structure is usually due to insufficient attention to the details of what? 1. Connection. 2. Deflection. 3. Erection problems. And 4. Foundation settlement. Connection. So bolt, rivet, and so on. Okay. Deflection. The deflection property that we compute and we learn from theory of structure. That is what we meant by deflection here. So the same thing. Okay? Erection problem meaning if we are doing the actual construction, we are putting up all the parts and doing the assembly. Okay? Okay? And because we are doing the assembly, we forget to use what? Substantial false work. We still need the false work. Although false work is the problem of concrete, in steel construction, we still need to use those on a limited scale, but proper. So false work has to be designed properly, particularly when we are doing high-rise building. Okay, and foundation settlement is, of course, very much timing again. One of the most problematic aspect in doing structure. Okay, rarely, if ever, do steel structures fail due to faults in the material. Material will not fail us because, of course, the bonding of iron to iron is 4,000 KSI. So substantial capacity to handle loads. Okay, but rather the failure is due to improper use. Our improper use, for example, during the construction, connecting the members to each other. Okay. Okay. So forgetting about deflection and connection, foundation settlement. So those are improper use. So common mistake in connection design. We neglect forces acting on the connection itself, such as the most common one is twisting, because we usually consider what? Axial forces, but sometimes we miss out on moments or twisting moments. Okay? For example, in a truss, members have been designed for axial forces only, but the connection may be eccentric. Okay? The connection may be eccentric, so we need to consider and use the proper set of formulas. Okay? So without which, it would result in increased stress, and ultimately, if we are not careful, failure of the structure. Another source of failure occurs when beam supported walls have sufficient bearing or anchorage. Okay? Sufficient bearings on the walls. No? Imagine a beam of this type supporting a flat roof on a rainy night when the roof drains are not functioning properly. So, can you see the reasoning behind? Okay. So, rainy night. So, there are what? There are risks, there are possibilities of water being trapped on the structural elements, okay, and will affect the physical characteristic of the structure element itself. For example, it will sag. Right? So as the water begins to form puddles on the roof, the beam tends to sag in the middle. So when we are having what we call that slab roofing. So when we have slab roofing, we can experience that, and the slab will form a sag in the middle, causing a pocket to catch more rain, okay, which create more beam sag and so on. So it will increase the sag, then create more pockets, then catch more rain, and then become even greater sag, and then catch another, and so on, continuously deteriorate, okay, negatively. Okay. Foundation settlements cause a large number of structural failures. Most foundation settlements do not result in collapse, but they very often cause unsightly cracks and depreciation of the structure. So even if that is not dangerous, the mere presence of crack on the structure will what? Will wreak fear from the occupants. So imagine if you are one of the occupants and you are seeing crack here, crack there, and crack anywhere, everywhere. So you will be what? Feel unsafe. Okay. So in structural analysis, uneven settlements in statically indeterminate structure may cause extreme stress variation, just like what we learned in theory of structure. So indeterminate structure. So we need to have a determinate structure rather than indeterminate. Okay. So the effect of uneven settlement, if really is a problem and cannot be cured, so we need to redesign and reanalyze using determinate structure. Okay. So not just analysis, after analysis, implement it to the real construction, to the actual construction. Meaning the connection between important structural elements must change from indeterminate to determinate structure. Okay. And also, because of this, we have a notion that designers or engineers would like to encounter settlement that is even, or the settlement is balanced in with respect to the whole building, meaning they settle at the same time, at the same pace, right, at the same rate. Okay. So if the settlement is imbalanced, okay, balance, so it will cause substantial amount of parasitic elements, forces, meaning, and the outcome would be fatal sometimes. Okay, disaster. Okay, so the usual structure, when completed, is sufficiently braced with floors, walls, and connections, and special bracing. But there are times during construction when many of these items are not present. Okay, so if they are not present, sometimes we just neglect it during the construction. So there are plenty of actions in during the construction that we neglect. Okay, as previously indicated, the worst conditions may well occur during construction, and special temporary bracing may be required. Okay, so because we know that these are still, we neglect that they need forms or false works. Okay, so bracing, such. Okay, one example. Support. So some structure failures occur because inadequate attention is given to number one, deflection. Number two, fatigue of members. Number three, bracing against swaying. Number four, vibrations. And lastly, the possibility of buckling due to compression member or compression of flanges of beam. So these are the list of common, very common problems or causes of failures. Again, that's the last slide. And for our challenge problem, let us use some scratch or answer this directly on the comment section below. Problem number 39, the pattern of reflectorized rubble strips shall finish within blank of any hazard it is associated with. So again, there is what? Typo error. This is supposed to be rumble. The pattern of rumble strip, not rubble strip, rumble strip shall finish within blank of any hazard it is associated with. What can you say about the pattern? It is within A, 250 meters, B, 100 meters, C, 50 meters, D, 150 meters. Okay, so that's all for this video. Again, this is Dr. EYPEI, preaching engineering for national building.